Okay, I'm going to pick up where left off yesterday. So yesterday I spoke about jet stirred reactors and flow reactors. Now I want to talk about the shock tube and RCM contribution to chemical kinetics. Okay, backwards. Okay, sorry. Why is it? Okay. So I'm going to skip through here. You've got a 4-stroke engine. There's an intake stroke, compression stroke, power stroke, and expansion stroke. And that's just it again. Okay, but what I want to do is just talk about this for a second. Here we have in-cylinder pressure, and this is versus crank angle degree. And this is for a diesel engine because the end of compression is 80 bar, right? And so the pressure is high, all right? And you can see the pressure reaches a maximum actually slightly before TDC, but above TDC. And then the pressure stays constant for about 5 crank angle degrees, and then the pressure rises due to ignition. Okay, so the thing is, what is the time scale? So crank angle degree actually can be converted into time. Okay, so what we're really looking at is pressure versus time. But what is the time scale? Okay, so I often say to my students, look, I drive my car, it's a diesel car, and when I'm cruising, it's about 1,500 revs per minute, right? If you look at the revometer. Okay, and so what is that in terms of how long does a compression take? Okay, so 1,500 revs per minute is how many per second? It's 60 into 1,500, so it's 250. Okay, so it's 1/25 anyway. The time for one revolution is 1/25 of a second, so it's 0.04 of a second. So is that 40 milliseconds? Okay, so it's 20. That's for a full revolution. So the time to go from bottom dead center to top dead center is 20 milliseconds. Okay, so what's 10 degrees here? If we convert that into time, I don't know, 180. I don't know. Pardon? Yeah, it's less. No, it's less. Much less. It's about 1 millisecond, I think. Right, 10 crank angle degrees is about 1 millisecond, I think. Right, I can't remember exactly. Okay, but the point is that if we want to do studies then, which are relevant to engines, we have to be in that time scale. We have to be in the millisecond, microsecond time scale. If we're not, then we can't do, well, we need instruments to do that. And that's why we use shock tubes and rapid compression machines in combustion, because they're the relevant timescales to combustors. In engines, really, the shock tube, but in the RCM, for gas turbines. Okay, so this is a picture here of the Galway RCM just after it was about to be commissioned. So it's a nice brand spanking new photo. It's not as clean as it is now as it is there. And then this is an old photo of a shock tube in Galway. Okay, I have slightly different now. Here we have the jet stirred reactor and we have the flame burner. Okay, so here's a close-up of the rapid compression machine. We have, here is the chamber, and it's a dual piston machine. So we have a piston inside the sleeve here and a piston inside the sleeve here. We draw the piston back, and I'll do more of it. So we draw the pistons back. We charge the hydraulic chamber with hydraulic oil, and then the piston shoots forward. It compresses the gas into the chamber. The gas reacts and eventually auto-ignites. Okay, so this is the pressure time history. So we have actually, I don't know why minus 40 here, because our compression time is about 16 milliseconds in our dual piston machine. Okay, and then the pressure rises to the end of compression, and then from the time of the end of compression when the piston stops to the rapid rise in pressure due to auto ignition is what we record as the ignition delay time. All right, and so there's a problem here though in the RCM, because you can see, well, it's not that clear, but you can see that there's the pressure reaches a peak and then it decays in time. Okay, and that's due to the facility effects, because we can heat the rapid compression machine, we'd say, to about 120 degrees. We could start maybe at room temperature, but a lot of the time it's preheated, sometimes around 100, 120 degrees C. And then, but when we compress the gas, the gas can be compressed to temperatures between 600 and about 1,000 Kelvin. So the gas is at a much higher temperature than the wall. And then so at the end of compression, the gas is losing heat to the wall. And the amount of heat it loses to the wall depends on, it's not constant. It depends on the nature of the mixture. If we're using argon as the diluent, the heat loss is a lot higher because the heat capacity of argon is much lower than that of nitrogen. And CO2 is better because, again, the heat capacity of CO2 is quite a bit higher than nitrogen. Okay, so it depends on the diluent gas. Okay, so then this is just a close-up of the chamber. Inside the chamber are the rods, and then we have the piston heads. And you can see here the pistons are creviced. So there's like a 4% taper in the piston head here, allowing the boundary layer gas on the wall to flow past past the piston, the tip of the piston, and into the crevice here, so that we don't have a roll-up vortex. And I talk about that here. And then this is just, so the chamber is actually rotated 90 degrees. This is looking at it though flat on, so the piston head comes nearly flush with this part, and the other piston flush with the face on the other side. Okay, just so you can see. Okay, so this is just a problem then. So here we have the right-hand piston, it's coming forward. And if we have a crevice piston, what happens is the boundary layer gas on the inside of the sleeve, okay, gets entrained into the crevice if we have a crevice piston. If we don't, and it was actually Simon Hajgreb and a student, his surname was Lee, working at MIT when she was there, that did a study, and they postulated this, that you should use a crevice piston when you're using an RCM to account for the roll-up vortex. Okay, so that's what we do. And if we only have a flat piston, what happens is the boundary layer gets entrained into the center of the chamber, we get a roll-up vortex, and then we get an inhomogeneous temperature field inside the rapid compression machine. Okay, and this is just a simulation then from Judith Wormel and John Simi performed 20 years ago, where this is just a half cut through the RCM, but this is using a flat piston on the left and a crevice piston on the right. And what we see is we have a piston on either side, and what happens is using the flat piston, the boundary layer gets entrained into the center of the chamber, and it ends up we have 4 quadrants of gas inside the chamber. At the center of each quadrant, the gas temperature is higher, but entrained into the center of the chamber is the cold boundary layer gas. And so we don't have a homogeneous temperature field inside the chamber at the end of compression with the flat piston. But with the crevice piston, you can see here's the crevice. The boundary layer has become entrained into the crevice here, and now the temperature field at the end of compression is much more homogeneous. And I believe anyone that's doing RCM simulations now use crevice pistons. I don't think anyone is using flat pistons anymore. Okay. So, and then this is just some PIV using flat piston heads, and to show, to kind of prove, so what I just showed you there was a CFD simulation, right, using star CD. So this is then just actually experimental evidence of the particle image velocimetry using flat piston heads. Okay, I don't know if that's playing very smoothly, but were you able to see? So it's playing again. And you can see that there's a lot of turbulence and roll-up vortex going on in that simulation. Okay, and then if I move to the next one, okay, and this is using the crevice piston, and hopefully you'll see that we have a kind of a flat front with the gas coming on either side. Okay, and then it does peter out, and there is a little bit of turbulence at the end. But by and large, you see that there is a plane of symmetry in the center of the RCM, and you don't have nearly as much turbulence and mixing going on. And you don't have that vortex. Okay, and that proved, we've never published that, but that proved that what we're, you know, the CFD simulation. Okay, so that's, and then this is just comparing both. You have this in your, so the flat piston experiments at different times, and this is just multiple, this is 1, 2, 3 different experiments showing the evolution as a function of time, okay, from 0 to 30 milliseconds. And then with the flat piston heads, or sorry, the crevice piston heads, you see that we have a plane of symmetry in the center here, and it's much more homogeneous and no vortex, and it's a lot cleaner. Okay, so I think that's really nice to show. Okay. Okay, so here, if I just go back, so okay, we have, here we have plotted pressure versus time. We actually use a pressure transducer, so we convert the pressure into actual units, okay, at the end. It's just a signal, okay? So, as I said, in our RCM in Galway, because it's a dual piston machine, the compression time is about 16 milliseconds. If it's a single piston machine, it can be like 30 or 40 milliseconds, all right? But anyway, here we reach the end of compression. Then the time to the rapid rise in pressure due to ignition, we report as the ignition delay time, okay? And of course, in an RCM simulation then, if we want to simulate this, we have to give an initial temperature and pressure. So what do? We actually give the room temperature and pressure, and we simulate the compression and expansion when we do the simulation, okay? But when we do that, we actually take a non-reactive profile, okay? So here, sorry, so we take a non-reactive experiment. So here we have the volume divided by the initial volume, okay? And you can see, okay, so we reach a maximum volume, or well, sorry, this is the pressure. We arrive at a maximum pressure, and then the pressure decreases. Apologies, this is the pressure, of course, okay? And so this part is compression up to the end of compression, and then this part is the pressure drops due to heat loss. It's mostly heat loss. There are other facility effects too. There could be some slight blow by the pistons and so on, but the vast majority of the facility effects is heat loss due to the gas losing heat to the walls of the chambers, okay? And what we then do is convert that pressure time history into a volume time history. So we have this relationship P2 over P1 is equal to V1 over V2 to the gamma. We know gamma, it's about 1.3 whatever, but we can calculate the gamma of the gas. Well, we use fixed frozen chemistry when we do the calculation. Okay, but you can see the start off, and for a large part of the compression actually, the volume doesn't change very much. It's only in the last few milliseconds that the volume decreases to its minimum, okay? Because you're compressing, okay? And then what we do is, by converting this pressure time history, which is a facility effect heat loss to the wall, mostly, what we treat it like it isn't a constant volume simulation anymore. It's like as if the pistons are moving back slightly, okay? And the volume is now increasing again a bit, okay? So that's how we simulate that heat loss or the pressure drop, okay? And remember, in an RCM, we cannot use a thermocouple because the dynamics are such, the timescales are such that you wouldn't be able to measure the changes. Kinetics is really sensitive to to temperature, okay? Exponentially dependent on temperature. And we really need to know the temperature as accurately as we can, okay? And the only way we can do measurements in the RCM accurately is to measure the pressure as accurately as we can, okay? So we measure the pressure as accurately as we can. We convert that instead of a pressure time history, we convert that into a volume time history. And then we use the volume time history of the non-reactive profile to account for the facility of the physics, basically, the compression, and we'd say expansion, but it's actually heat loss mostly to the wall at the end of compression to account for that. And then we plug that into, this is just to say, look, we don't take every point on this blue line because there's like 10,000 points or something. So we just take points, we take as few points as we can where nothing's changing, and then as many points as we can where things are dynamic and changing a lot, and then few points again along the curve, okay? So that we can do an efficient simulation. And then in Chemkin, we include the volume profile, the non-reactive volume profile as the input in our simulation, okay? And that accounts for the physics that's going on in the RCM. And then whatever happens after that should be due to the chemistry when we do the simulation, okay? So that's how we simulate the RCM, okay? So this is just a plot showing, well, you've got the facility effect and the chemistry, you combine them, and then you can do your simulation, okay? We can assume in an RCM that the temperature and pressure are related by this. So you have T final or just T, whatever temperature you're at. But T final over T initial is equal to P final over P initial to the power of gamma minus 1 over gamma. All right? If we take that, okay, and we have that. So actually, Jackie Sung and his group, a long time ago now, 13 years ago, published this paper in Combustion and Flame. And what they did was they used two-line thermometry and a H2O measurement in an RCM using laser absorption at 7.6 micrometers to measure the temperature inside the RCM, right? So here's the normalized absorbance versus wave number, and this is due to water. So they have a mixture of argon with 2.87% water used in a single pass RCM setup, okay? And here's the profile that they see at 663 Kelvin. Here's the profile that they recorded at 8096 Kelvin. Here's the profile that they recorded at 1008 Kelvin. And then if you interpolate between those lines, you can get other temperatures, okay? And so if you measure the line absorption comparison of three representative cases, so if you measure the absorption due to the water inside your RCM, you can actually measure the temperature inside the RCM. And so that's what they did, okay? And so here are two different measurements. So they had a compression ratio here of 14.3, a compression ratio here of 10.3. The points here are the experimental results that they measured in the experiment for the absorbance and the temperature, basically based on the absorbance. And then the blue line is the simulation, performing the simulation the way I just described it for you, okay, previously, okay? And you can see that the points lie perfectly along the line, okay? So actually the way we're doing it, it proved that the way we were doing it, we were doing, using these blue curves, right? But he actually went and did the experiment to show that that was actually quite accurate, okay? And that's the experiment, Okay, so and the paper is there if you're interested in reading it. Okay, so so that's the RCM. Okay, and other people, I don't have the slides actually. I normally do. People have done speciation measurements in RCMs as well. Okay, maybe I'll have that a bit later. We check. Okay, so reactions in shock waves then, in shock tubes. A shock tube, we can access a wide range of temperatures and pressures, maybe up to about 2000 Kelvin. And it's a nice facility. That's not a great slide. Okay, well, I go back one. Okay, a shock tube is a facility. It's just what it says on the tin, right? It's a long tube, normally cylindrical. I actually used a rectangular one when I was doing my PhD 30 years ago. Okay, it's quite small, and it was made of aluminium. Okay, but typically they're stainless steel cylindrical tubes, and depending on the thickness of the walls of the tube, you can reach different pressures, and they can be rated to higher pressure. The one we have in Galway, I think, is what is it rated to? I think it's like 500 atmospheres or something like that. Okay, but it's a tube, and it's divided into two parts. Okay, so we have, it's not well represented here, but typically there's a diaphragm or a flange here, and there's a diaphragm that separates the driven section from the driver section. So what we typically do in the business, we prepare a test mixture accurately in a vessel, right? And then we evacuate this down to very low pressure, maybe 10 to the minus 3, 10 to the minus 4 of a torr, all right? And then we add our test mixture into the tube, right? And that would be a relatively low pressure. So let's say about 1 atmosphere in here of test gas, okay? So that's our fuel air mixture or our fuel diluent mixture, okay? And then that part of the tube is separated by a diaphragm. In the higher pressure ones, it's typically aluminium, from the driver section. And then into the driver section, we add maybe about 30 atmospheres of helium, okay? And then we burst the diaphragm. So when we burst the diaphragm breaks very quickly, and that, because of the pressure differential, so we have 30 atmospheres of gas on this side and just 1 atmosphere on this side, it generates a shock wave which passes through the gas, heats it, compresses and heats it to a higher temperature and pressure. That shock wave reaches the end plate, reflects back, and heats the gas to an even higher temperature and pressure. And that temperature and pressure we can calculate, and typically we can get temperatures and pressures that are relevant to combustor conditions. Okay, so that's the idea of it. Okay, so this is just showing, again, the dynamic pressure sensing with a shock tube. So this is representing the high pressure section here. We have a higher, it's more dense, so it's higher pressure gas. We have pressure transducers in the wall of the tube, and typically we have one in the end plate here. And we have a membrane which separates the driver section from, driver section from the driven section. And so when the membrane ruptures, and that's actually what the diaphragms look like when they break, the aluminium ones, it sends the shock wave reaches the sensors, and it sends signals back via the pressure transducers. Okay, so the reason we have pressure transducers along the wall of the tube is because we want to measure the shock velocity at different locations and then extrapolate the shock velocity to the end plate. If we know the shock velocity at the end plate, we know the initial temperature and pressure of the gas, and we know the gas composition, we can actually accurately calculate the temperature and pressure behind the reflected shock wave. Okay, and so that's why we need the pressure transducers. Okay, so
how do you rupture the membrane?
So what we do is actually, it's a little bit more complicated. We have here we actually have a separate section, okay? And so what we do is, it's just a very small section, I don't know, maybe 1 or 2 centimeters wide, okay, only, okay? And what we do is, we might have 1 atmosphere of gas on this side, and then what we'll do is we fill this part and that 1 or 2 centimeter wide section to about 15 atmospheres. And the diaphragm can still resist that quite easily, can resist that pressure. And then what we do is we stop filling this section, that middle section, okay? And we fill this section to 30 atmospheres, right? And then we have a separate connection to an evacuated cylinder, okay? A cylinder under vacuum. And we just evacuate the smaller amount of 15 atmosphere gas that's in this section from that section. So now we have virtually no pressure in there, 30 atmospheres pushing on it, and it ruptures the diaphragm, okay? Good question, and that's how we do it, okay? And then we get nice, clean diaphragms like you saw in the last video, you know, the petaled 4 ways. Most of the diaphragms look like that in real life, okay? So this is just another slide that I've gotten up that. So if I go back one, okay, so again, we have the high pressure driver gas. Here we have the low pressure driven section. The diaphragm bursts. The gas passes through here. It'll become yellow. The shock wave reflects off the end plate, and then it becomes red. And the color is to represent the temperature. Okay, so the higher the temperature, the stronger the color. Okay, and then we have a detector. So in the shock tube, right, it's always here at the end plate, okay, that we want to do the diagnostics. And I'll explain that in a second, okay? We don't want to be looking at gas here or any place else. As close as possible to the end wall of the tube is where we want to do our diagnostics, okay? And I'll explain that in a second. Okay. Okay, so here the tube, we have the reflected shock wave, and then here we have a pressure versus time history, okay? So here would be, prior to the shock arrival at the end wall, the pressure is very low, 1 atmosphere, okay? The shock arrives at the end wall, and there's a bit of ringing, like because it's a shock wave, right? And so you can see here the pressure jumps up, and then it equilibrates here to what looks like a little over 20 atmospheres, right? And then the pressure stays constant up to this point, and then it rockets up again, okay? So from the time of the arrival of the wave, the shock wave at the end plate, to the rapid rise in pressure due to ignition, we call that the ignition delay time. So what's happening in this time? If we do an analysis close to the end plate and we measure what's happening is, right, the fuel decomposes, right? Or formaldehyde is formed, right? And CO is formed, and CO2 is formed. And you can see the CO2 is coming. The CO has formed just before the ignition and so on. So we're getting all of these species formed in the time prior to the ignition, okay? So the fuel is being consumed. This is a nice video, or a nice picture of what happens, okay? So we have density, velocity, pressure, and temperature, all 4 of them happening in the shock tube. But I'm just going, let's focus on the pressure. So in the pressure, the high pressure, so here, at the difference between the high pressure and the low pressure, we have the diaphragm, okay? So the high pressure side and so here's the driver side, this is the driven side. We burst the diaphragm, the pressure rises, okay, to P2 and T2, and then it reflects off the end wall, and we get P5 and T5, okay? So we get a higher pressure again, okay? And the same if temperature. So the temperature on both sides of the diaphragm is the same. We burst the diaphragm, the temperature increases to T2. The shock wave hits out the end wall, and the temperature goes to T5, okay? Just conventionally, they're called P2, P2, P5, T5, okay? Okay, this is an interesting picture, okay? So it's shock position versus time available in a shock tube, okay? This point here represents the diaphragm, the point of the diaphragm, okay? And this is distance from the diaphragm, okay? So this represents the driver side, this represents the driven side of the tube, okay? So we burst the diaphragm, and what we're looking at here on the y-axis is time, okay? But this red line represents the incident shock wave reaching the end wall of the shock tube. When it reaches the end wall of the shock tube and it reflects back immediately, then our gas is at the reflected shock temperature and pressure. And that's the condition that we want to study, okay? And then the shock wave reflects back and hits the end wall at the other end of the tube and then reflects back off that again, okay? But to every action, there's an equal and opposite reaction. So when the shock wave is generated, we have what's called an expansion fan, which travels in the opposite direction down to the other end of the tube from the diaphragm. That expansion fan hits the end wall at the other end of the tube, reflects off it, and then travels down to the test side of the tube, okay? And that will eventually arrive at the end wall of the tube. When that expansion fan, the wave from that, hits the end wall, that's the end of the time that we have available to study reaction in the shock tube, okay? Now, Professor Hansen at Stanford has put inserts into the tube so that he can extend this time to longer time, okay? Or if I go back one, maybe go back two. Sorry. The longer the tube is, okay? So if we have a big, long driven section and we have a long driver section, then we'll have more time, the more time we'll have. So typically, you know, the shock tubes are 3 or 4 meters long at least, right? Because you want to have the time scale to do the measurement, okay? So what's limiting you is the time from the arrival of the shock wave, well, the incident wave and the reflection of that incident wave off the end wall to the arrival of the expansion fan, okay? And that can be, this time scale can be extended by making the driver section longer, right? Or making the whole tube longer, okay? So we have a tube now where our driver section, we've extended it so that we can have longer test times in the tube, okay? I hope you can understand, okay? So that's a nice diagram to explain what's going on. So here then we're looking at the business end of the tube, and I got this slide from Eric Peterson. We have here a slit in the tube, okay? This is the end wall. We have what you call a window in the end wall here. We have a window in the side, another window here, and then we can have a photomultiplier detector with a filter, maybe at 310 nanometers to measure OH radical, for instance, or a filter at 431 to measure CH radical, all right? But anyway, whatever we want to look at. But if we look at the sidewall, what we're doing is we're looking at the test gas that is in line with the window inside here. So our incident wave hits the end wall here, reflects back. Now we're at the reflected shock temperature and pressure. and the gas is sitting here, and it starts to react. So unimolecular fuel, the fuel undergoes unimolecular decomposition, hydrogen atom abstraction, radicals form, intermediates form, and then all of a sudden you get so many radicals and so on that we get autoignition inside the tube. And we can measure then the ignition delay time of the mixture that we're studying. Okay? And if we do that, we can see, if we look at the light emission on this side, nothing happens for a period of time, and then we get a big rise in light emission from OH, and then it drops again. Why? Because the layer of gas that's in line with the window ignites, and after it's ignited, all the fuel is gone, and so we don't see light anymore. But if we look down the tube, it's different. We still have the same delay in time, ignition time. Then we have a rapid rise in light emission, but the light emission stays fairly high for a considerable period of time. Why? Because we're looking at multiple layers. So remember, the shock wave reflects off the end wall, hits this pocket of gas first, or the first gas molecule that's at the wall first, then the one that's next to it, then the one that's next to it, and so on. Okay? So by the time you get even to the gas that's here, they get hit slightly later, whatever time it takes for the shock wave to hit them. They're hit slightly later in time, but if they all have the same characteristic delay time to ignition, right? They're all igniting with that same delay, but because they were hit later, they're igniting that little bit later. Okay? And then we see this light emission continuing for a period of time if we look down the tube. Okay? I hope I've made sense there. Okay. But typically in Galway, we measure ignition delay times, and here's one this is a slide of courtesy of Eric Peterson, which he took for propane in air at 1,000 Kelvin and 30 atmospheres, 5.5 in air. Okay, and you can see here's the arrival of the shock wave at the end plate, rapid rise in pressure. The pressure increases, I don't know, is it 30 or 35 atmospheres, something like that. And you can see the pressure stays relatively constant. That red line is just to see that's a constant, a vertical line. And you can see that the pressure is fairly constant. There is some noise, but then we get ignition. Okay, and then this is the light emission due to CH. Okay, at 431 nanometers. Okay, so you can see that they're coincident. And then the ignition delay time is the time from time zero here, the arrival of the shock wave at the end plate, to the rapid rise in pressure or the rise in light emission. Okay, and we measure that as the ignition delay time. So this is a nice, clean experiment, okay, where we can rely very much on the data. And then if we can take data from the rapid compression machine, we can take data from the shock tube, and if we just look at these data at 30 atmospheres, these are old now, but this is work that we did with Rolls-Royce years ago, maybe 20 years ago in Canada. So this is for a 90% methane, 6.6% ethane, and 3.3% propane mixture at 5.5 in air, okay? And what we can see is, look, the shorter times, so from about 2 milliseconds or 1.5 milliseconds, 2 milliseconds, down to, I don't know what that, 90, 80, 70, 60, 50 microseconds, we're measuring data in the shock tube, right? From about 2 or 3 milliseconds all the way up to 20, 30, and sometimes 300, okay? Not on this graph, okay? We can measure timescales in the RCM, okay? And so with that timescale, then we can actually do a wide range of experimental temperatures, okay? Because of the timescale. So reactivity is typically lower at lower temperatures. The ignition delay times are longer, and then they're shorter at high temperature. So we have the ability to be able to do both shock tube and RCM experiments in Galway and extend the range from very low temperature, 600, 700, all the way up to 1600 Kelvin, okay, which is really nice, okay. And so you can get, I've plotted the RCM data here as open symbols and the shock tube data here as solid symbols, okay. Okay, so ignition delay times are an important indicator of fuel reactivity. They can be measured as a function of temperature, pressure, equivalence ratio, and dilution. The RCM, we can measure time or ignition delays approximately in the range 600 to 1100, and the shock tube 1100 to 2000. But remember, it's based on the time available in the facility. It's not the temperature range per se, it's the time range of the facility. Okay, so just to bear that in mind. Okay, but it converts to a temperature range ultimately. Okay, and the problem, but okay, so there's actually then some problems with them. I just want to show this. Okay, and there's maybe a slightly interesting story around this, if you indulge me for a second. So I was in Livermore, and I left Livermore in 1999 and went back to Galway. And there was a student working with John Simi at the time, and she said, look, is there something that she had been working on the RCM, but she had just started, and she was starting to do, and I said, look, there's nothing on propane available in the literature, and I'd really like to see, can we test the model against propane data? So she took these propane data, which are these green symbol experiments. And at the time, you can see there's some, there's some wide range in the measurements here, but by and large, you can see the data are here. Unfortunately, when we plotted these data at the same temperature as available ignition delay data in the literature that were measured in Wales, I can't think of the guy's name. It'll come to me maybe. And also from Christoph Schulz's group in Duisburg, you can see that the ignition delay times measured in the shock tube are almost 2 orders of magnitude faster, shorter than the ignition delay times that we measured in the RCM in Galway. Okay, and at high temperature, the line is the model prediction. Okay, and at the time, okay, I didn't know how to explain this, right? Except the model, I didn't have to do much to it to get good agreement with the RCM data. And I just couldn't do anything reasonable to the kinetics in the model to get agreement with the shock tube experiments. So I felt, okay, there's something wrong with the shock tube experiments, okay? And the agreement with the RCM isn't perfect, but it was a lot better, okay? So there's issues, okay? And actually at the time, I actually published that. I went back, I published that in 2007, right? And at the time, it was normal to get about 3 reviewers to Combustion and Flame. We had 5, right? And all of them said, well, we're not sure what to do, and they were sort of hemming and hawing whether they'd accept it. But anyway, they did, and it was published. But this, and I said, look, I don't know why this is. I can't explain it, but this is it. Okay, so this is again the slide that I just showed you a few minutes ago, where from the shock tube, where we measure the pressure rise. The blue is the pressure signal. The red line is just a vertical line there. You can see that the pressure is very constant, and then we have ignition. Okay, so this is a standard ignition for propane at 56.5 and 30 atmospheres. Okay, but if we look at some other ones, if we look at a methane-ethane mixture here, what we see here, again, we see the rapid rise due to the arrival of the shock wave at the end plate. The pressure stays constant for about the first 4 milliseconds, okay? And after that, the pressure starts to go up until it reaches 6 milliseconds. And then we have this rapid rise in pressure before ignition. So we don't have this constant pressure situation, right, prior to ignition, but we have, like, we'd say a 1, 2, 3-stage pressure rise, right? Or, well, we have a constant pressure, then a slight pressure rise, and then a really steep pressure rise prior to ignition. If we assume, can you just picture in your mind's eye, if we assume that the pressure is down here throughout, then our simulation is always going to be too slow for this experiment, right? Do you understand, right? Because we're assuming when we simulate, if we didn't take this pressure time history into account, we're assuming that this pressure stays flat to here, right? And then it rockets up, as it does in this diagram here, or in this experiment, okay? But it's not doing that in this experiment. The pressure goes up. What happens when the pressure goes up? What happens to the temperature? Yeah. And if the temperature's gone up, what happens to the kinetics? Faster. Why? Because the kinetics are exponentially dependent on temperature, right? And look at the pressure rise from here to here. It's nearly at 60 bar. And you're simulating 20, but it's actually at 60. Okay? So what was happening, if I go back one, what was happening in these experiments, but wasn't reported, were those pressure rises prior to ignition. So there's facility effects in the shock tube too. And some of them are understood, and I'll go through it with you, but some of them are not still, right? So, sorry, these experiments suffered, or for want of a better word, from pre-ignition pressure rise, early pressure rise. And hence, they're faster. Okay, now if we take a model and consider the facility effects. So if we have a chemistry model and we simulate the compression and expansion, we'll say in the RCM, the facility effects in the RCM, and we consider the facility effects in the shock tube, we can simulate the data well, and then we understand. So we did this subsequently, years later, right? So here again are the shock tube data, here are the RCM data. The green line is now simulating the RCM data with facility effects, and that's the green dashed line, right? The red dashed line is simulating the shock tube, including the facility effects, and then the solid line here is assuming constant volume. Okay? Yeah.
Examples of the facility effects in the shock tube.
Well, I'm just showing you here, the rise in pressure. I'm going to show you now in a second.
Oh, okay. I mean like the causes, like things that cause or lead to some of those.
Let's see if I answer your question in the next thing. And if not, I'll talk to you at the break. Okay? Or I can, okay, so here's then a plot. So actually, when I was preparing that paper on propane, I happened to revisit Livermore. I spent 10 weeks back at the lab. So I was in the Bay Area, and I was invited by Ron Hansen to give a presentation to C's Group, and I was telling them about the propane work. And they said, okay, that's very interesting, and they looked into it, okay? So they looked at this, and they also worked on propane as well, but this is a hydrogen-air mixture at 5.42 in the 3 to 4 atmosphere range, okay? And here they have data again. It's not a very wide range in temperature, actually. This is just ranging from, what is it, about 900 up to 1100, 1150 or something like that, okay? It's not a very wide range. But you can see, here's two conventional, well-known models, EURIMEC from 1999, and this is actually a model from my group from 2004. And here are data that were published in 1995. And here's some data that they published themselves from 2003, okay? And you can see here that neither model at temperatures above about 1,000 Kelvin can simulate the low temperature data, okay? Above 1,000 Kelvin, and that's kind of a rule of thumb, right? If you're above about 1,000 Kelvin, so if I go back, hopefully I can go back here. Again here, so you're at about the 1,000 Kelvin cutoff for whatever reason, right? You know, things become uniform and you don't have these facility effects occurring, right? At temperatures below that, they tend to for certain fuels. And here again, we're seeing it in hydrogen. Okay, and so then they looked at the pressure time histories that they recorded for the hydrogens, okay? And what they saw was that they had this constant dP dt of 2% per millisecond. Now, actually, if you simulate a dP dt of 2% per millisecond for most fuels, it won't make much of a difference in the prediction of the ignition delay time, right? But for hydrogen, it makes a big difference, right? And hydrogen is very sensitive to it, right? Particularly sensitive to it, I should say, right? And and here is, so to see it, there's actually two experiments performed here. One is the reactive experiment where you see this rapid rise in pressure, but also another one you can see here. That's a non-reactive experiment where they've replaced the oxygen with nitrogen, okay? And you can see that it's actually it's not in the chemistry, it's in the dynamics of the tube, right? And it's happening whether the system is reactive or not, right? At this condition, okay? And so then so what they did was they applied our equation again, which we use in the RCM. So in other words, if the pressure is rising, the temperature is rising. But you calculate the temperature rise from this relationship. And when you do that, right, and you apply it to this graph, you get this dashed line. And now, actually, it's going straight through the experiments. And that was using, I think it was using GRI-MEC. I don't think they used O'Connor, right? So, but it doesn't matter. The O'Connor one would have given you the same good result anyway, right? So you have to be careful is really what the point, and include these facility effects. So that was one thing. So that's a facility effect that for that fuel and at that condition, the pressure tends to rise at 2% per millisecond. But you can simulate that and then simulate your result with an accurate model, okay? I hope that answers the question you asked me, okay? However, if I go back to, I don't think, if we go back to this one, okay? So this could be considered a dP dt, right? But it's actually not constant. You can see that it was constant up to about, we'd say 4 milliseconds, as I said before. Now it starts to rise, and then it rises, okay? I don't think this is fully understood, right? And it would be nice to know what causes it. We don't yet fully, right? But if, as an experimentalist, you see it, you should report it, because otherwise we won't, as a community, be able to simulate your data. Okay, it's really important that that's reported, and that. So actually, I'm encouraging my group now to always provide the pressure time histories in the supplemental data from both, measured in both the RCM and shock tube. Okay, so that people can see them.
Thanks. I have a question. In the second plot, in the second plot, how ignition delay time is measured? Is it from 20 bar until tau ignition?
It's from this point, from this time here to that time there. It's defined there. Is that what you're asking?
No, I'm not asking in this plot. The previous one, early pressure predictions.
Sorry.
Early pressure rise. So
what it would be, what we would do in a good question. I'm sorry, probably didn't explain properly. Okay, so thanks for your question. Okay, so here the pressure reaches 20 atmospheres, let's say. So what we say is, okay, we can calculate the reflected shock temperature and pressure. So in our simulation of the shock tube, what we do is we include the fuel mixture composition, okay, the pressure and the temperature, and then we say, okay, it's a constant volume simulation. Go now and process the chemistry based on that premise, okay? And if we do that, right, we're correct in the simulation up to about 4 milliseconds. But thereafter, we're simulating a pressure that's down here. But in the experiment, it wasn't. It's up here. And then from about 6 milliseconds, it's rocketing at a different rate altogether, right? And if we don't include that in our simulation, our predicted ignition delay is going to be much longer than what is measured experimentally. Do you understand? Because experimentally, the pressure is going up, and simultaneously then, the temperature is going up. If the temperature is going up, the kinetics is exponentially dependent on that, and so you're going to have an exponential increase in the kinetics as well, okay? But you're not simulating that correctly, okay? And if you're not simulating it correctly, what you're going to see is that's your simulation, and that's the experiment, okay? And you're going to be completely off, okay? So, and Professor Hansen might be upset if I say this, right? But I think, look, hopefully not, right? What I'm trying to say is, and I've shock tubes. I have 2 shock tubes in my lab, and I have 2 RCMs in my lab, right? And the thing is that you need to be careful what you're doing, right? No experiment is perfect, right? And the reason I was saying Professor Hansen might be, probably under a lot of conditions, the shock tube is more perfect than a rapid compression machine. But you need to be careful that it is and report it if it isn't, okay? And be careful with the data, really, okay? And he is, right? So, good, I'm glad. And another thing that Professor Hansen has done is really pioneered laser absorption measurements in shock tubes. And I'm not going to go into it big detail, but again, you're on the business end of the tube. You may generate intermediates or whatever it is during the experiment, and then you use a laser to measure the concentration. And you use the Beer-Lambert law, essentially, I is equal to ECL. So the absorbance is proportional to the concentration of whatever intermediate you're aiming at, ultimately. Okay, I've got lots of slides on that and too much detail, but that's essentially what he does. So this is just looking here. You have to be careful what you're doing. So at 1 atmospheres, this is the ratio as a function of temperature. You see slightly higher profile at 2 atmospheres versus temperature. This is absorption coefficient and times the pressure product, okay, for CO2 transition. So you need to be aware that it does increase as a function of pressure so that you're not over reporting the concentration of the species, okay? So the absorption is changing as a function of pressure, and so you have to account for that. And then, so you have online absorption is this dashed line. The offline absorption is this, so there's some background absorption is really the point. And then you have to subtract the background from what you're measuring to actually have a corrected absorption due to CO2. That's really what I'm trying to report. Okay, I think I'm including these, but Amir Farouk, who now himself has advanced this technique more and more in KAUST, and he's done a lot of excellent work there using a laser absorption too. He's done it, but it's very useful technique because what you can do is you can measure concentration profiles as a function of time at different temperatures. So here we're looking at methyl acetate. CO2 is one of the, if we have any of those methyl esters, CO2 is one of the major products produced from methyl esters, okay? And it gives it's a good test of the chemistry model to check to see is the chemistry model matching the profiles that you measure or not, right? And so measuring the CO2 mole fraction as a function of time at different temperatures is very useful to modelers to know whether or not their mechanism is accurate or not, okay? And here again, This is for a different fuel, but it's this methyl propionate. But again, it's the same thing. You're measuring CO2 as a function of time at different temperatures. Okay, and if the model can capture that, then you can be. It's an indication that the chemistry is right. Okay, but it's very valuable to have these species profiles because they're specific to particular fuels. They're just more details. I'm not going to go into them. You can measure other things too. This is another one. Okay, I'm not going to show it. This is just showing that sometimes there's overlap, and you have to be able to, of different lines, and you have to be able to subtract them from one another to get specific species. So here's looking at ethylene. Okay, so I don't want to go into it. Okay, this is a kind of a famous work from Subhath Vasu. He worked with Ron Hansen, published in 2009, and this is for dodecane. Okay, so species time histories, and again, this is pioneering. Like this is done 15, 16 years ago, but at the time, this was very pioneering to get simultaneously 1, 2, 3, 4, 5 different species. Okay, and to have this amount of species, not just ignition delay time, but to have species profiles as a function of time is really helpful in validating the chemistry model. Okay. Okay, good. So this, okay, so Subhath. So, and then this is just a kind of a synopsis. I got this from Professor Amir Farouk, and it just shows the different species that can be measured at the different wavelengths using the different lasers. Okay, but it's all very similar. The laser absorption, the absorbance is proportional to concentration. Okay, and you have to be careful and know what you're doing. But if you do, you can actually provide very valuable data. Okay, and not only that, but Amir Farouk has one of the major things that he's done over the last 10 years at KAUST is measure the rate of different fuels plus OH, right? Using this technique. Okay, one of the most important reactions in combustion, and I'll be talking about that very soon, right, is H plus O2 gives O plus OH, okay? And here we're looking at H2O absorption, okay? So absorption due to H2O. So we have typical pressure and laser transmission histories in a reflected shock tube experiments. The upper one is at this condition here, 0.1% O2, 0.9% hydrogen, in 99% argon at that temperature and that pressure, and then you have a different one. Okay, so here you have pressure, and here you have transmission. But this is transmission due to H2O. Okay, and if we look at the reactions to which H2O is very sensitive, what you see is for experiment A and B, you can see in both cases it's a little bit sensitive. What's this? H plus O2 plus M giving HO2 plus M. But it's extremely sensitive to H plus O2 gives O plus OH, that profile. Okay? So to simulate that profile, we have to, the rate constant of the H plus O2 giving O plus OH reaction is very important. And there's probably been multiples of tens of millions of dollars spent on measuring the rate constant of that reaction because it's the most important reaction in combustion. Right, so what he did then is he measured. So this is water concentration in experiment A and experiment B as a function of time, and the profile you can see it somewhat here, but not so much later. And then that black solid line is the best fit of H plus O2 giving O plus OH, okay, to the water concentration line. And then this dotted line and the dashed line are the predicted profiles using a 10% faster or 10% slower rate constant than what they measure. Okay, so the point of this slide is that you can actually use the laser absorption diagnostics and the profiles to back out a ray constant, right? Because the ray constant is very sensitive to, at this condition, or well, this condition is very sensitive to that ray constant. The prediction is very sensitive to that one ray constant, right? And so you can actually back out the ray constant. And from that, they reported this ray constant here, the red line. Okay, here are some of their new, I don't know where their new data is. This is, okay, sorry, their new data is down here. There were some higher temperature data here. And you can see actually the O'Connor model, which is I was part of, right? The ray constant is too high at high temperature. And you can see actually down here, there was some uncertainty, and it was reasonable for us to extrapolate, but actually these other data showed that that ray constant was, we were too high, okay? But again, it was very useful to see that, okay? So shock tubes and RCMs are complementary. Understanding the connections of fuel oxidation, they help in that by helping us measure ignition delay time. I didn't show we can get speciation data, I suppose, with the laser diagnostics, but in the RCM tool we can by doing, I didn't show it, but we can. And sometimes we can actually get elementary ray coefficients also, okay, from them. Okay, so let's take a break and we'll come back at 3:30 if that's okay with everybody.